Imagine you're standing on Earth, holding a piece of chalk. You let go. It falls. Simple, right? Gravity pulls it down. But here's the thing. Gravity isn't pulling at all. That chalk isn't being pulled down. It's following the straightest possible path through space that's been curved by Earth's mass. You think the chalk is accelerating downward, but from the chalk's perspective, it's just moving naturally through warped space. The ground is accelerating up to meet it. That's Einstein's insight. Gravity isn't a force, it's geometry. Space itself is curved, and objects follow that curvature. Now take that idea to the extreme. What happens when you pack so much mass into such a small volume that space doesn't just curve, it collapses? You get a black hole. And at the center of that black hole is something called a singularity. A point where all the mass is compressed to infinite density, where space curves infinitely, where Einstein's beautiful equations break down completely and spit out nonsense. Infinity. Division by zero. Mathematical disaster. Subscribe and like for more videos that explain what's really happening beneath the surface. Let's start with what a black hole actually is. You've probably heard that it's a region of space where gravity is so strong that nothing can escape, not even light. But that's not quite the right picture. It's not that gravity is pulling harder. It's that space itself is falling inward. Imagine a river flowing toward a waterfall. If you're a boat drifting downstream, there's a point where the current becomes so fast that even if you paddle at full speed, you can't escape. You're swept over the edge. That point is called the event horizon. For a black hole, the event horizon is where space is falling inward at the speed of light. Inside that boundary, space itself is moving inward faster than light can travel outward. That's why nothing escapes. Not because gravity is strong, but because there's no path through space that leads out. Now imagine you're falling toward a black hole. As you approach the event horizon, something strange happens. To someone watching from far away, you appear to slow down. Your clock ticks slower and slower. You never actually reach the horizon from their perspective. You're frozen in time, asymptotically approaching, but never crossing. But from your perspective, nothing feels unusual. You sail right through. Time feels normal. There's no barrier, no wall. The event horizon isn't a physical surface. It's just a point of no return. Once you're inside, every direction you can move points toward the center. Forward in time now means inward in space. You can't stop moving toward the singularity any more than you can stop moving forward in time. And as you fall, tidal forces start tearing you apart. Here's why. Gravity isn't uniform. Your feet are closer to the black hole than your head, so they experience stronger gravity. They accelerate faster. The difference stretches you. The technical term is tidal force, but physicists call it spaghettification. You get stretched into a long, thin strand. For a small black hole one with the mass of a star, the tidal forces near the event horizon are enormous. You'd be ripped apart before you even crossed. But for a supermassive black hole millions or billions of times the mass of the sun, the event horizon is so large that tidal forces there are gentle. You could cross the horizon intact and not even notice. But as you continue falling inward, the forces grow. Eventually, they become infinite. That brings us to the singularity. At the center of the black hole, according to Einstein's general relativity, all the mass is compressed to a single point with infinite density. Space curvature becomes infinite. Time stops meaning anything. The equations produce infinity, which is math's way of saying, I don't know. Physicists hate infinities. They're red flags. They mean your theory has reached its limit. Here's the deeper issue. General relativity describes space and time as smooth, continuous fabric. But quantum mechanics, the other pillar of modern physics, says everything is grainy, jittery, probabilistic at the smallest scales. These two theories work brilliantly in their own domains, but contradict each other at extremes. A singularity is that extreme. It's a place where the smooth geometry of relativity collides with the quantum jitter, and we don't have a theory that combines them. We don't have quantum gravity, so we don't actually know what happens at the singularity. Maybe the singularity isn't a point. Maybe quantum effects prevent infinite compression, creating some kind of exotic quantum structure instead. Maybe space and time themselves dissolve into something more fundamental that we don't yet understand. The singularity is where our maps of reality end. It's not that we can't measure it because it's hidden inside the event horizon. It's that our theories break down. Nature is doing something there, but we can't describe it. Now, here's where it gets even stranger. Stephen Hawking discovered that black holes aren't actually black. They radiate. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear near the event horizon. Normally, they annihilate immediately, but if one falls into the black hole and the other escapes, the escaping particle looks like radiation. The black hole is evaporating extremely slowly. Over unimaginable timescales, far longer than the current age of the universe, even supermassive black holes will evaporate completely. But there's a paradox. If a black hole evaporates, what happens to the information about everything that fell in? Quantum mechanics says information can't be destroyed. But if the black hole vanishes, taking the singularity with it, where did the information go? This is the black hole information paradox, and it's still unresolved. Some physicists think information is encoded on the event horizon itself, that the three-dimensional interior is somehow represented as two-dimensional information on the surface. This idea is called the holographic principle, and it suggests reality might be fundamentally different than we perceive. So when you ask what's at the center of a black hole, the honest answer is, we don't know. The singularity is where our best theories fail. It's a placeholder for ignorance, not a description of reality. And that's okay. That's how science works. You push your theories until they break, and then you figure out what comes next. Here's the philosophical takeaway. Black holes are nature's way of telling us we're not done. We don't have the final theory. There's something deeper, something that unifies gravity and quantum mechanics, something that explains what really happens when space and time are pushed to their limits. The singularity isn't an answer. It's a question mark. And somewhere in that question is the key to understanding reality at its most fundamental level. You've never understood black holes until you accept that even our best theories can't fully describe them. That's not a failure. That's a frontier. And the universe doesn't care if we're ready. It just keeps existing, waiting for us to catch up.